Good morning. Today we are doing lesson 8.5. Hopefully in class I have already read this book to you so you know kind of an idea of what we are learning about today in terms of exponential growth. So in the past everything we've done is linear, meaning we have straight lines that we've been graphing. Now everything that we're going to be doing is exponential, which means we're going to have curved lines. Our lines are going to increase slowly and then really fast by an exponential rate. So we always read graphs just like here. We read slope, this one would be positive from left to right, and this one would be walking downhill or negative. We read exponential graphs the same way, from left to right. So this one, as we go, is going up, so we call this exponential growth. And then from here, left to right, we're going down. This would be called exponential decay. So this is like positive and negative, but we just use different words to describe it. This one, as we go from left to right, is going down. So this is also called decay. And from here, left to right going up would be called exponential growth. So we're going to take a look at some tables to write an exponential function. So an exponential function is a function in the form y equals a times b to the power of x. I'm just going to write that over here. Y equals a times b to the power of x. So notice the x is the only thing that has an exponent, or the b is, not the a. So it says where a cannot be 0, so it's not multiplied by 0. And b has to be greater than 0, meaning our number here has to be 1 or 2 or 3 or something. And b cannot be a 1. We can't have an exponent of 1, otherwise we're not growing, we're not going anywhere. So don't worry about this so much, just know that this is our function or equation, y equals a times b to the power of x. So these are called nonlinear functions because they're not lines. So they're just asking us to compare a linear function to an exponential function. So in the past, we've had, like for example, y equals 3x plus 2. They got this where we begin on our graph when x is 0, y is 2. That was our b where we began our graph. And then the pattern, whatever our pattern was, for example, plus 3, plus 3, plus 3, plus 3, that was our m or our slope when we were to graph this. It's our pattern of what we're doing over and over and over again. Like if we were to graph this, this would be rise 3 over 1, rise 3 over 1, to form a nice straight line. Now, we have to look at what we did from the linear function and compare and now figure out how do we get this equation y equals 2 times 3 to the power of x. So we really, in this equation, need to find a and we need to find b, because x and y are just part of the equation. So just like we found b back here is where we began, this one, a, is where we begin because it's really in alphabetical order. Think of, first I'm going to find a. I'm looking for when x is 0. And then b is what I'm going to do over and over and over again. See how b is 3? And our pattern each time is multiplied by 3. It's kind of hard to tell on this side, but over here 2 times 3 is 6. 6 times 3 is 18. So b is what we're multiplying over and over and over again. Think of that as the base to your exponent. It's what we're multiplying. Like this would be 3 to the power of x, because our b is a 3. And then a, right there, where x is 0. Oops, not the letter a. We want, a is really the number 2. So that would be a 2 times 3 to the power of x. Again, b is our base to our exponent, what we're multiplying over and over and over again, the exponent one. So let's look down here at a couple examples. We need to find a first and then b. These are two separate problems. So a, it says what the value of y is when x is 0. So first here, x is 0 right here. So a is really 27. And then b, what is being multiplied each time? The base to our exponent. So each time we go from left to right. What are you doing to get bigger numbers? Well, 3 times 3 is 9. 9 times 3 is 27. That's b. So our equation in this form right here is going to be y equals a, which is really 27, and then times b, which is really 3 to the power of x. You can't multiply 27 times 3 because if we were to do the order of operations, we would have to do our exponent here before we can do multiplication. So you have to leave this just like this. You cannot multiply those. So let's take a look at our next one. A is when x is 0. Right here, a is going to be 8. And then b is what we're multiplying each time. So from 2 to 4, well, you just multiply by 2. 4 times 2 again. 8 times 2, yes, it works. So this is b. So our equation is going to be y equals, and then a is 8, times b, which is 2 to the power of x. So it's 2 to the power of x, and then whatever times 8. So that's our answer. This is what we call an exponential equation. We have a couple more that we're going to practice. Alright, so next we have, first we need to find a. So here's 0, so a is really just the letter or the number -1. And then b, what's multiplied every time. To get to -1/16 to 1/4, we're really going up. This is a bigger slice of pie or something. And then over here, we're going up, we're going up, we're going up. We're multiplying. It's easier to tell over here, multiplying by 4 each time. And you know it's going to be multiplied every time because it's an exponent. It tells you how many times you're multiplying the same thing over and over and over again. -1 times 4 is also -4. So it works going across. If you want to double check this in your calculator, you can. But I know b is going to be 4. So my answer is y equals a up here, which is really -1, times b, which is really 4, to the power of x. That's our final answer. Same thing here. A, 0's over here this time, is 5. And then b, our base to our exponent, what we're doing every single time, 5, 10, 20, 40, we're multiplying or doubling this, multiplying by 2, which makes sense because 5 over 2 times 2 would give us 5. So that makes sense. So we have y equals a, which is 5, times b, which is 2 to the power of x. Alright, last two down here. A right here is just 5. Always a first where we're looking for 0. And then b, the base to our exponent. Look at the numbers that it's easier to tell. 5 and 15. Okay, well 5 times 3 would give us 15. Okay, 15 times 3. Yep, it works to get us to 45. So here, multiplying by 3 will also work. 5/9 times 3. If you want, you can multiply by 3. It'll give you 15 over 9, which will simplify to 5 over 3. So we know that's going to be b. So we have y equals a times x to the power, or a times b to the power of x right there. So a is 5 times b, which is 3 to the power of x. Last one here, I would like for you to try this on your own and then click play to see if you got it right. A right here is going to be a 9. B, what are you multiplying each time? The base to our exponent. 1 times 3 is 3. 3 times 3 is 9. So we know we're multiplying by 3. That's going to be b. So we have y equals a, which is 9, times b, which is 3, to the power of x. X and y are always just x and y. Now we're going to take something that is in exponential function, which is y equals a times b to the power of x. This is really, a is just really a 1 here, so they don't really show a as being 1. But if you want to know, this is an exponential notation. But in order to graph this, we don't have any strategies, so the only strategy I would say that we do have is to make a table. So I'm going to make an xy table, x, y, and I'm going to plug in some numbers on each side. I'm just going to make my table here quick. Our graph on my x-axis goes, we have 0, we have 1, 2, 3, 4, and then y we have -1, -2. So I'm going to stick with 0 and then a couple negatives and a couple positives. So -2, -1, 0, 1, and 2. All I have to do now is plug in these numbers in for x up here and figure out what y is to plot my points. So I'm going to take my first number. Well, actually, it doesn't really matter what order we go in, so I'm actually going to plug in anything to the power of 0 because this is something that we actually know. 10 to the power of 0, anything to the power of 0 is just 1. So you shouldn't really need that one, your calculator for that one. If you want, you can do 10. Remember, this is to the power of 0. Will give us 1. Then I'm going to plug in the next one, which is 10 to the power of 1. Well, 10 one time is just 10. And then over here, 10 to the power of 2. Remember, I'm just plugging in what x is right here, and x is a 2. So 10 to the power of 2, 10 times 10 would be 100. And then I need to go the other direction as well. We would have 10 to the power of -1, which really means you're going to take that and move it to the bottom of our fraction, which if you wanted to, you could just say is 1 over 10 to the power of 1, or 1/10. If you plug that in your calculator, 10 to the power of -1, that would give you 0.1. If you want to write that as a decimal, sure, you can. Either one will work, so you can write 1/10, or you can write, I'm going to move this down a little bit, 0.1. And then 10 to the power of -2 would be 10 to the power of 2 in the denominator. Now we moved it to the bottom. So 1 over 100, or 0.01. So all we have to do is plot our points. So here's x and here's y. So I'm going to start at 0 here in the middle. At 0 we're up 1, and these go by 2s, so 1 would be right in the middle here. Plot a point there. Then at 1 we're up 10. 2, 4, 6, 8, 10. And then 2 up 100, we're not going to be able to graph that because this graph only goes to 14. And then on the left side here, at -1, we're at 1/10, which is really close to the line. But at -2, we're even closer to the line at 1/100th. All of these are going to get super, super, super close to 0, but we were never actually going to touch 0. We're just going to get super close to it. So when we draw our line through, it's going to be super close. We're going to go through our points and then straight up. So it should form a nice curve. This is kind of jagged, but it should form a nice curve. This is an exponential growth function. Let's try the same thing with the next one. All we have to do is graph it. So I'm going to make an XY table. So here's x and y. Same numbers, it's easy to plug in -2, -1, 0, 1, and 2. Because those numbers are on here already. 0, 1, and 2 for x. And we're going to plug that in for x right there. So first we have 5 over 2 to the power of -2. Then we're going to have 5 over 2 to the power of -1. 5 over 2 to the power of 0. And then 5 over 2 to the power of 1. I'm just writing these out. If you can do this in your calculator, that's fine. We know this one, anything to the power of 0 is 1. So I'm going to plug this next one into my calculator. Remember, this is in parentheses, so I need parentheses in here as well. So I have 5 divided by 2 to the power of 1, which is really just 5 divided by 2, because anything to the power of 1 is just that same number. So I have really 2.5. Then I'm going to do it to the power of 2. So 5 divided by 2 to the power of 2 will give me 6.25. Then I need to the power of -1. -1 really means we're going to flip these around, so it should be 2 over 5 or 2/5. But I'm going to plug it in anyways, just to make sure. To the power of -1. Yep, 0.4, which is 2/5, which is fine, either one. And then last, 5 over 2 in parentheses, 5 divided by 2, to the power of -2. gives us 0.16. As you can see, going to the left here, we're getting closer and closer to 0, but we're never going to go 0 and we're never going to get to negative. So if we plot these points at 0, we're up 1. Remember, this is really what A is. This is A where we're beginning our graph, and then to the right and to the left are our pattern, multiplied by whatever. So at 1, we're up 2.5, so here's 2, 1, 2.5. At 2, we're at 6.25, so here's 6.25 would be a little bit higher. At negative 1, we're at 0.4, so 0.5 would be in the middle, a little bit less. And then at 2, we're at 0.16, so super close to the bottom or the edge. So we're going to make my line go super close to the edge, through our points, and then right up this direction. This is hard to draw a nice curve on here. Don't just connect the dots, because that's not what we want. We want a nice curve. Okay? I don't want to see this and dots connected. Nice curve. Okay? Let's do 2 more just like this. I'm going to make myself a table. Oh, one thing we forgot to do back here, it says identify its domain and range. Domain is what we're plugging in. We could have plugged in any number we wanted for x on either of these. So our domain is simply any number. I'm going to say all real numbers, because we could have plugged in any number for x this way or any number for x this way. It doesn't matter what we plug in. Same thing here. For all of these, your domain is going to be all real numbers, because we could plug in anything on our x-axis. We could plug in any number in for x up here. But y is our range values. Remember, the letter y is right in here, that's why it's our range. So our range is our y values. Our y values got super close to 0 here, but they're all in the positives. Notice we got super close. They're all positives, all positives, all positives, all positives. We don't have any negatives. And you can see that from here as well. All of these are positive numbers from really small all the way up. So we're just going to say all positive real numbers. Same thing here. These are all in the positives, so it'd be all positive real numbers. So let's go on to the next one. I'm going to make myself some tables. Make a table over here while I'm at it. And I'm going to put my x and y, and the same numbers we like to plug in. -2, -1, 0, 1, and 2. We could have plugged in other numbers, but it's nice to fit in the middle of our graph. Because as you can tell in the last ones, if we plugged in numbers way over here, well, that's not even going to be on our graph, so it's not even worth it to plug those big numbers in. So we have -4 to the x. Notice there's no parentheses here, so we have the -4 to the power of x, and x is first, a 0. So if you're not sure, plug this one in. So we have -4 to the power of 0, which is a -1, because this, anything to the power of 0 is 1, but then it's negative, so it's a -1. Then we have 4 to the power of 1, and it's negative. If you're not sure, again, plug it in. -4 to the power of 1 is -4, yep. And then we have -4 to the power of 2 is -16. And that makes sense, -4 squared. Over here we have -4 to the power of -1. I'm just going to keep plugging them in my calculator. -4 to the power of -1 gives me -0.25. And last, -4 to the power of -2 is -0.06. I'm just going to do the first 2 decimals. -0.06. So I'm going to plot my points. At 0, I'm at -1, so x is 0. We didn't go left and right, we just went down 1. And then at 1, we're down 4, so at 1 to the right, we're down 1, 2, 3, 4. So So we plotted those two. At 2, we're down 16. I can't plot that. So at -1, I'm at -0.25, so there's -0.5, so 0.25 would be right about there maybe. And then at -2, I'm at -0.06, so super close to the x-axis. So I'm going to draw my line through here. A nice curve. We didn't go above, but we're right at the x-axis there. So the reason why this one is flipped down is because we have this negative right there. So I'm going to look at our domain. First, what did we plug in? Well, for x, we could have plugged in anything we wanted, so we can choose all real numbers. We could have picked anything on our x-axis to plug in, either way. And then our range, or our y values, are only in the negative side. There's nothing in the positive, so our y values, our range, are all negative real numbers. This next one, I'm going to actually have you try on your own, and then check with me or check with a neighbor. I'm not going to go over this one together. So next we're going to graph 3 graphs, and we're going to compare each graph with the original, which is y equals 2 to the power of x. So this is our same chart that we have. We're just only for right now going to look at the first 2 columns, just like our xy table. So we're going to compare this graph to these two. So first, anything to the power of 0, I'm going to first plug in for x is 0. Anything to the power of 0 is 1. Then we have 2 to the power of 1. Anything to the power of 1 is just that number, so it's 2. And then we have 2 to the power of 2. 2 times 2 would give us 4. Then we have 2 to the power of -1. If you're not quite sure, let's plug it in. 2 to the power of -1 gives us 0.5. And then finally, 2 to the power of -2 would give me 0.25. I'm going to erase these ones so they don't confuse us here. So those are our first numbers with 2 to the power of x. But now we have the same exact thing, 2 to the power of x, and it's just multiplied by 3. So instead of plugging the same thing in multiple times, I'm just going to take this column and multiply it by 3. So 0.25, or a quarter, 3 times would be 0.75. 50 cents 3 times would be $1.50. 1 times 3 would give us 3. 2 times 3 is 6. And 4 times 3 is 12. All I'm doing is taking what I have from the first column, 2 to the x, and multiplying it by 3. Well, this last column is 2 to the x again. It's also multiplied by 3, but it's just a -3. So we just need to take this column and now make it a negative. Negative 0.75, negative 1.5, -3, and -6, -12. And then we just simply need to graph these two. So first, let's graph this one. I'm going to graph this one in blue. So I'm going to start with 0 up 1, 1 to the right up 2. At 2, we're at 4, 1, 2, 1, 2, 3, 4. At -1, we're at 0.5 in the middle. And then at -2, we're at 0.25. So I'm going to draw my line through there. This is not a very good curve, but do your best. Then I'm going to do the same thing, plotting this next one. If you want, if you would only have a pencil, maybe label this one 2 to the power of x. Our next one at 0, we're up 3, right there. At 1, we're up 6. Well, 6 isn't going to fit on here. 4, 5, 6 would be like right off the graph there. So I can't even plot 12. But at -1, I'm at 1.5. And then at -2, I'm at 0.75. Oh, this is not a very good line. Try and draw a nice curve there. It should be the same exact curve, just up a little bit. And then the last one, as you can tell, this one has a bunch of negatives, so it's going to be on the negative side. So at 0, we're at -3. At 1, we're at -6, which isn't going to be on our graph here. At -1, we're at -1.5. And then at -2, we're at -0.75. So this one again is the same as the red one, except it's flipped upside down. So we just need to do this one last word, which says compare to the original. So this one, compared to the original, it's multiplied by 3, which is what we're going to call a stretch. And compared to the blue one, it's stretched up, which we call a vertical stretch. So that's all I need to say there. But now the green one, this one was also a vertical stretch because it was multiplied by 3. The number out in front, which is really a, remember, because this is a times b to the power of x, a, that number, there 3, is also a stretch because it's stretched away from the 1 where it normally would be at. So we also call this a vertical stretch. Because it's the same as this red one, the only difference is there's a negative, which made our graph flip from a +3 to a -3. So we call that a reflection, like a mirror. It flipped over to the other side. So we need those two words, vertical stretch and reflection. Alright, I know this is a long lesson, but this last piece is almost identical. We know the formula y equals a times b to the power of x. The only difference now is b is really 1 plus r. So this is what we call an exponential growth model. I don't really care what all this says, you just need to know what each of the pieces are. So this is a formula that you're going to use when you're talking about investing or growing anything. It could be growing a tree, it could be investing money, anything like that. A is the initial amount that you start with. Oftentimes it's going to be money. A is your initial amount, and so A I tie to the word amount. And then this is your growth factor. We know it's growing because it's a plus. And then R, that letter 1 plus R, R is the growth rate. How fast are we growing? Maybe at the bank you're going to grow at a 1% interest rate or something like that. Notice the growth rate is always going to be written as a decimal. And then finally T is the time, which makes sense. And down here I had our little note, make sure you wrote the rate as a decimal. So here we're just going to do 2 problems, I believe, with this, and they'll be pretty quick. So here's our equation again. It says you put $250 into a savings account. Okay, that's going to be our initial amount, or A. We're initially investing $250. That earns 4% annual interest. Okay, our interest rate has to be written as a decimal. So 4% as a decimal is 4% out of 100%, which is also known as 0.04. You can plug that in your calculator. 4 divided by 100, it'll give you 0.04. So there's our rate. And it says it's compounded yearly. You do not make any deposits or withdrawals. How much will your investment be worth after 5 years? So that's our T. Time is usually in years. So we're going to plug in everything in. Y equals A, our initial amount is $250. And then 1 plus our rate, which is 0.04, meaning we're going up by 0.04, after 5 years. So if you want to simplify this, we know 1 plus 0.04 is 1.04. Order of operations tells me to do my exponent first. Remember PEMDAS? We got to do our exponent first. So in my calculator, I'm going to plug in 1.04 to the power of 5. And then I'm going to leave that in my calculator and I have to multiply by 250. So times 250. Y is 304.16. Which matches B. Last one is exactly the same. It says the owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. So this was our initial investment, our A. The value of the car increased at a rate of 6.9% per year. Okay, That's 6.9% out of 100%. So if you're not sure, well, 6.9 divided by 100. As a decimal, that would be 0.069. So just for right now, I know A is 11,000. Oops, 11,000. That's an initial amount. And our rate is 0.069. So we're going to first just write an equation over time. We don't know what t is, so we're just going to leave it as t for right now. So y equals a, which is 11,000, and then 1 plus the rate, which is 0.069, to the power of just t, because we don't know what the time is. So this is part A, we did. Now part B, the auction took place in 2004. What was the approximate value of the car at the time of the auction? And round to the nearest dollar. So we're going to write out our same equation, 1.069, but t in 2004, well, since 1984, if you're not sure, 2004 minus 1984, well, or you can just count 84 to 94 to 2004 would be 20 years. 4 minus 4 is 0. 200 minus 198 would give you 20. So our time is 20 years. So we could just plug this whole thing into our calculator. 11,000. And then in parentheses we have 1.069 to the power of 20. Should be 41,777.9. Oops, what was that? 41,777.9. But it said round to the nearest dollar, so I'm going to round that up to $41,778. I apologize for that lesson being a little bit long, but good luck on, your homework.